A heavy steel turbine shaft spins at 3,000 RPM. Then, without a single warning from the monitoring software, it shatters. The failure is catastrophic, and the statistical anomaly detection model completely missed the physical precursors. Traditional anomaly detection relies purely on statistical correlation and historical data mapping. It observes a system, establishes a baseline of normal behavior, and raises a flag when current data deviates from that mathematical pattern. In an industrial setting, an alert outputting an 87% anomaly probability is operationally useless. Engineers cannot shut down a production line or replace expensive hardware based on a percentage. They need a physical root cause to investigate. A deterministic approach analyzes the centrifugal pump by tracking exact physical mechanisms. Instead of a generic probability score, it identifies a specific fault, like bearing outer race spalling caused by lubrication contamination. Predictive maintenance fails when reliability engineers cannot safely act on statistical guesses. They require auditable mechanical proof. Building trusted, mission-critical industrial AI requires a strict architectural demarcation between diagnostic reasoning and language generation. This diagram shows the first layer of that architecture. The physics rule engine executes diagnostic reasoning deterministically, without machine learning. The second layer is the large language model. It is isolated from the logic, restricted exclusively to translation, semantic retrieval, and orchestration. To prevent AI hallucinations in high-stakes environments, the system must treat physics as the absolute source of truth, and the LLM merely as the user interface. Hard-coding failure thresholds directly into application code requires full software redeployments for every update. This introduces systemic risk and limits how quickly engineering teams can adapt to new fault patterns. This diagram shows the Integrated Master Schema, or IMS. 8 relational tables store over 451 physics rules as parsable data. A single row links a specific asset directly to a known failure mode, a sensor rule, and a prescribed reliability-centered maintenance decision. A custom recursive descent parser evaluates these conditional expressions at runtime. It reads the logic safely without ever executing an eval command that could expose the system to arbitrary code execution. This data-driven architecture allows engineers to instantaneously extend the diagnostic knowledge base by adding rows without touching the backend microservices. Encoding rules as parsable data is the only way to achieve complete auditability and deterministic traceability from the sensor to the screen. These compressors generate raw telemetry data. That data enters a sequential, forward-only pipeline mapped directly to the ISO 13374 standard, which defines the processing levels for condition monitoring systems. A raw telemetry event enters Module A, the signal guard layer. Noise or sampling violations trigger a soft penalty, degrading the quality score. The penalized data moves to Module B for physics role evaluation. The low initial quality score mathematically caps the final diagnostic confidence. This strict mathematical compounding ensures the system is honest about uncertainty, preventing multi-million-dollar false alarms triggered by degraded telemetry. In chaotic industrial environments, transient sensor spikes routinely cause alarm fatigue in standard monitoring systems. This chart illustrates state transition hysteresis utilized within the Module C fusion engine. A severity score must exceed the upper threshold for multiple consecutive evaluation windows before the machine's health state is formally escalated. By making it mathematically harder to trigger an escalation than to de-escalate, the architecture forces the AI to prove persistent instability before requesting human intervention. At the UI presentation layer, the diagnostic copilot acts strictly as an orchestration and translation interface. The first step of the Retrieval Augmented Generation, or RAG, workflow is entity extraction. RAG is a method that gives an AI access to a specific database to provide more accurate answers. The system identifies a specific asset ID from the user's natural language query. This flowchart demonstrates using the extracted ID for a direct database lookup, bypassing the LLM to fetch deterministic matched rules. In parallel, pgvector performs a 768-dimensional semantic search to retrieve relevant causal factors. These structured data points are then assembled into an immutable prompt context. The LLM operates under absolute constraints. It is barred from inventing failure modes outside the IMS, and it is forced to append specific rule citations for every generated sentence. This strict RAG architecture effectively strips the LLM of its ability to diagnose. It reduces the model to a highly articulate translator for the underlying physics engine. Accurately diagnosing a failing component is ultimately a reactive measure if the underlying equipment design contains a structural error. Track 3 of the RAPID architecture introduces contradiction-driven engineering, driven by Module G. The system analyzes chronic failure loops to identify structural contradictions. For example, it detects when a bearing clearance specification mathematically conflicts with its operating thermal growth. Industrial AI achieves its highest value by generating the engineering evidence required to redesign a part so it never fails again. Abandoning statistical pattern matching in favor of deterministic physics allows for immediate day-one deployment without the need for historical training data. True reliability engineering requires an architecture that treats physics as the absolute ground truth. Predictive maintenance is a misnomer. The true purpose of industrial AI is to understand the physics of failure so completely that we transition from predicting breakdowns to permanently preventing them.